Welcome to a lesson with Dr. Powell. Let's find the centroid of this triangular region. At least let's compute what x bar is. So, um, and the same type of process that we use for x bar, we could use for y bar here. We're going to use the 1/3 rule for triangles. But to do this, we need a base to work off of that's perpendicular to the x direction. So we can just draw this one. Then we have two triangles. So that means that we can go 1/3 of the distance this way to get the centroid of this region, 1/3 of the way this way to get the centroid for this region. So 1/3 of the way this way for this region would be, so we're going from an x value of 0 to an x value of 3. So it looks like it would be 2, because we have 3 total and 2/3 of the way this way, or 1/3 of that way. So it's going to be an x value of 2. So the x bar for this region is 2. Maybe I'll call this x1 bar maybe. Then what about this one? We're going to have to go 1/3 of the way this way. So this goes from an x value of 3 to an x value of 4. So it looks like we're going to be going 1/3 of the way this way, so 3 1/3, or 10/3. So x2 bar would be equal to 10/3. So we automatically have an x bar for both of these triangles. Now the only question comes, how do we put these together to make the centroid for the whole entire region? The answer to this is weighted average. And this can kind of be seen by what's happening. If you think about the integral that we need to work with this region, the integral that we need to work with this region, if we add these two integrals together, maybe because of weight, we have some weighting issues, but really we have the same integrand. We just have kind of different weights going on. Let's think about that. So over here, we would have 1 over the area of that region, so call it area 1, times the integral, and then what's inside here is actually this, what's inside here is going to be very similar. The only difference here, I guess, is in the specific definition of dm, but it is the same. But you could kind of think of the dm as being for the whole shape if you want to. It just changes form over here. So it's the dm as we move from here to here. So, but basically we're going to have x dm. And the definition for dm may change from triangle to triangle, but it'd still be dm for this whole thing as we move along, which is important to realize. So for the first guy, the centroid calculation is this. For the second guy, it's something like this. Now here, where the mass is going from here up till here, or from here to here. Now when we change variables in terms of x, so we'll have something right here with a dx and something else here with a dx, and as we change, this will actually be the integral from 0 up until this point at 3, and this will be from 3 to 4. Okay. Now, it'd be nice to have an integral, though, that goes from all the way from 0 to 4, which we kind of do if we finagle this just slightly. So if we were to multiply this guy right here by A2 over the total area A, and this one by A1 over A, notice what happens. The A1s cancel, A2s cancel, we get 1 over A, 1 over A, and we can add these. Then we have a constant that we can factor out, and we can add these two integrals, or at least we can connect them because of the bounds, and just let this little squiggly denote whatever the dm is as it changes from here to here. So we get x, so quite literally that turns into the dm portion for the whole triangle. It's a piecewise definition, but it still works. And so this is the dm for the whole entire triangle, the bigger one, and you get 1 over a. So you actually get the x bar for the whole thing. Notice what we did is we have to multiply so this right here is x1 bar. This is the actual centroid x value, x. So we're actually taking a1 over a times x1 bar, and we're adding it to a2 over a times x2 bar in this, and then this weighted averaging of these two will actually be equal to x bar. It's kind of like doing this. This bit of area is, what fraction is it of the total area here? Well, it's a1 over a, right? It's a1 divided by a. That's the fraction of area that it is, and we're going to apply that fraction. That's kind of like the percentage value that we're assigning to the x1 coordinate here, x1 bar coordinate. And this is the percentage of the area that's over here. These two percentages actually add up to 100% because a1 plus a2 is equal to a. And so this is called a weighted average. So much percentage for this guy, so much percentage for this guy, with a total percentage being 100%. And you do this in the multiplication. You think of this as a decimal times, or a percentage of, and then you add them together and you get the total weighted average, kind of a weighted average type deal. So without actually going through the integration, I only discussed that just so we could kind of think about how this will to motivate what we're about to do. So what we really need is we need to figure out what the area of the total is and what the area of the individual shapes are. And then we can use the centroids that we have right here to get everything that we need. So what is the area of this whole thing right here? We can do this in a couple different ways. If we really wanted to, we could just look at the full, we could look at this full full rectangle where this is sitting in, right? This is sitting in this whole thing right here. And this whole rectangle has, let's see, it's 4 by 4, it has an area of 16, right? And let's think about, so it has a total area of 16. Now we can kind of split this up and think about for a second here what's going on. I mean, well, okay, point blank, we could just do something really simple. We could take this right here. This is from the length of 3 up, and then 3 over, that's 9. Subtract off that region. This region right here has 1 and, well, actually it's not 3 and 3, it's 9 halves, excuse me, 9 halves, so 3 and 3, so minus 9 halves. This region over here, we're going to be, it's going to be 1 by 4, so an area of 2, because it's a triangle. Here have 4 and 1, so area of 4 divided by 2, so 2. So we're subtracting, so this has an area of 2 over here. This has an area of 2 over here. This has an area of, say, 3 to 3, so 9 halves. So we subtract those off and we get the area of the total, if we will. So getting the area of the total, we have, so minus 4, and then this is 4.5. So minus 8.5, so it'd be 7.5, which so 7.5, which would be the same thing as 15 halves. So 15 halves is the total area. Then what's the area of the individual triangles? So well, this triangle right here is 2, because this is 2, so this would be 2 as well, but minus this little sliver right here that we have to worry about. Okay, now what is that? So we think about this, this is a slope here, and we're going over, so when we go over 1, well, when we go over 4, we've gone up 1. So if we go over 1, we've gone up 1/4 of the way. So this goes up to a fourth, and it goes over 1. So it'd be 1 times a fourth divided by 2, so it'd be an eighth. So this is really a little eighth in there. So it looks like area 2, which is this part right here, area 2 is going to be 2 minus an eighth. All right, then let's compute. Okay, 2 minus an eighth, let's work that out specifically. That would be 15 eighths. Okay, so A2 is 15 eighths. Now what's A1? All right, so let's compute what A1 is. A1 is going to be okay, so we can think yeah, I mean, I guess we can compute this in a variety of ways. I mean, this is kind of nice here, the way this is set up. We could even go like this if we wanted to, and just think of, in fact, if we draw this line, we'll notice something very nice with this shape. Let's see, almost nice with the shape. Okay, well, kind of, yeah, because if I draw a line right here over, so this part is 1/2 of that rectangle. This part is 1/2 of that rectangle. So the area is 1/2 of the rectangle from here to here. So we can just find, so that would be from here to here, that's 3 over. And then from here to here, this is actually 3 3/4 because we're taking a fourth off. So 3 times 3 3 3/4, which would be 13. 13 quarters, 13 fourths. Okay, so 13 fourths from here to here. Is that right? Let's see. Did I get that right? I just want to make sure I got that right. No, hold on. So 3. I didn't do it right. So what is it? 3 3/4 would take us to. Sorry about that. So this is right out. So 3 3/4, that'd be 12. Yeah, that should be right. 13. It should be 3/4. I wrote 1/4. That was my mistake. Okay, 3 3/4 from here to here. 3 3/4, which would be 15 fourths. Okay, that looks a little better to me. All right, I was thinking just a fourth less than 4. Okay, so we have 3 times. Okay, so we have 3 times 15 over 4 would be that, and then we take that and divide by 2. So this rectangle area divided by 2 would be that region for A1. So we end up getting 45 over 8. Okay, so A1 is 45 over 8. A2 is 15 over 8. So let's look at these values for x1 bar and x2 bar and work through that. So x1 bar is 2. And we're going to multiply that by A1 over A, right? And we computed A to be 15 halves. And if we want to, we could think about what's going on again. We're doing A1 over A times x1 bar, so plus A2 over A times x2 bar. In this calculation, we could actually factor out the 1 over A if we wanted to. So we'll do that. We'll factor out the 1 over A. So 1 over A would be 2 over 15. Take a reciprocal, so factor that out. And then we're just left with A1 times x1 bar. So x1, and then plus A2 times x2 bar. So x1 bar is 2. So we have 2 times just A1, which is 45 over 8. And then we add 10 thirds for that x2 bar times A2, which is 15 over 8. All right, and then in the calculation, so we can distribute at least the 1 over 15 through. So this would become a 3, and then distribute over here would cancel out with that. So if we bring it, distribute here and here, cancel that out, this becomes a 3. And let's see, then we end up getting 4 times 3, so 12. 12 over 8 plus 10 over 3 times 8. So we can multiply top and bottom here by 3 to get 36 plus 10. So 46 divided by 3 times 8, which is 24, which we could write as 23 over 12. Over 12, right. So we just computed what x bar is for this particular triangle as 23 over 12. Now maybe there could have been a simpler way of doing this, going about this, but we were just wanting to illustrate the idea of weighted average and how we can work with it in taking certain, so the area in this part and what percentage it is and that part, and you can get the center of mass overall. In fact, the same basic idea even works if you have a system of shapes, that are in separate locations. Um, you can actually compute the center of mass of a system of shapes as well. You skip over just in your integration. There's like nothing here. It's like zero mass here for a while dm is, and then it picks up here. So it works the same way. You can weight your averages here by finding the centroid of one part, another part, and taking a weighted average, what percentage this area is of the total area versus the other. So this actually works well in those cases too. But we use this we use the 1/3 rule for triangles from a base, and then we used a weighted average to figure out what it was, because it wasn't so simple to get a base in these other cases. Thanks for watching.